Okay, thank you. So good morning to everyone. My name is Blanca Tejedor. I am officer and the secretary of the Data Sensing and Analysis Committee. And this session is prepared with my other colleagues, Dr. Alessandro Carbonari and Dr. Shabtai Isaac. This session is entitled Digitalization and Sustainability in the Built Environment. And the universities that participate in this organization are Universitat Politècnica de les Marques, Ben Gurion University of Negev, and Polytechnic University of Catalonia. This is the event schedule. We start with an introduction and presentation of keynote speakers, more or less 25 minutes from now. Later, we have 5 sessions. Each keynote speaker has 15 minutes to explain his topic. And later we has the part of the discussion where all the questions that arise during the presentations are concentrated here to dynamize more the discussion with young researchers, full professors, or people from the industry. Okay, why are we organizing this seminar today? So the European Council wants to link the industry with academia. And in the case of our committee, we want to identify effective ways to advance the state of knowledge and support existing and new conferences and scientific publications. A few months ago, we decided to create 3 work groups, and this seminar corresponds to the first one. We want to do an outreach activity to promote the first white paper of this technical committee, entitled Data Management at Urban Scale. The second group is to establish collaborations between academia and societies related to the industry. This task is led by Alessandro Carbonari. And the third work group is based on workshops and research activities to promote the mobility of academia staff, for example, professors, PhD students, or master students. And now we move to the context. According to the International Energy Agency, cities are responsible for 75% of global energy. To facilitate a urban transition to smart and sustainable cities, we should adopt a digitalization paradigm. This includes a reduction of environmental degradation, reliable energy management systems to provide greater flexibility and resilience to buildings, integrated multimodal transportation systems to reduce congestion and accidents, and real-time data for decision-making and urban planning, among others. So we know all the tools that we have. We have artificial intelligence, automation, smart meters, Internet of Things, but we know how to use these tools to achieve these blocks that lead to the digitalization paradigm. This is a question in the air that we want to try to solve. Nowadays, most of the cities present large sensor of networks. Enterprises invest on infrastructures. However, several questions can arise. How is the data captured and used? Should specific requirements be accomplished? Who are the main agents in the built environment? Can advanced modeling technologies support the retrofitting of existing built assets? This is why we are here today. We would like to discuss if we can enhance this scenario through our research and experience. In the white paper, we talk about enabled technologies for data collection and how digital twins can focus on built assets, and how the agents can participate in each domain. So to identify the enabled technologies for data collection and enhance some scenarios linked to building and transport networks, several interrelated domains were assessed in the operational stage of urban infrastructure systems. Pavement maintenance, urban building, energy modeling, construction safety management, health status monitoring of bridges, and traffic management. Now we start with pavement maintenance. The optimization of maintenance strategies can be based on the information extracted from this type of systems. PMMS is divided into 5 stages. Here we can see data collection, defect detection, defect severity evaluation, pavement condition index, and repair actions. Regardless the enabled technologies, PMS can adopt 2 approaches of models, the project level approach, bottom up, or the network level approach, top down. The first one is for lower level decisions based on maintenance and reconstruction, while the second approach is focused on high level decisions in terms of budgets and policies. So the difference between them is the use of more aggregated data and the need of calibration later, the analysis of the different scenarios. The main drawbacks that we have in this domain is that most of the Department of Transport don't consider all possible maintenance anomalies, and collected data depend on the technician expertise and available equipment. So here we add a human error. Another barrier is that there is a lack of international integrated PMS and a comprehensive decision support system. If we analyze in this domain, what is the capture data, what is the use, the requirements, and agents that participate, we can create this type of table. So for the pavement defects, we can analyze or characterize the materials of the pavement to prepare repair strategies or maintenance plans, estimate cost, and the more important thing is that we can determine the pavement condition indices, taking into account the severity and the type of the defects in the road. To achieve this, it's important to know the inspection frequencies and how the monitoring is carried out. The agents that are more interested in this part are road users, of course, the Department of Transport, the Transportation Agency, and centers of traffic management. When the capture data is the geospatial location and weather parameters, here we want to predict possible scenarios. Imagine that you have the road frozen and you have to decide how many tracks have to provide salt in the road for remove the snow or the ice of the road. So for the reason, it's important to know as well the influence of climate conditions to create heat and cold maps of the roads. So here we need real-time data for the weather forecast, for the traffic, and other parameters of our transport network. And here the agents are the maintenance staff and dots. In the case of traffic, the use of data is to know the transportation flow, the use of urban network, if incident arise in the network and something like that. And for this reason, it's important to know the real-time data and historical data to predict other scenarios. Here, more or less, we have the same agents that we meet in the other cases. Now we move to the urban building energy modeling. Is another domain that can enhance to the reform management and city development scenarios, but we have a big problem, a lack of building filters and users' privacy aspects. But regardless of this drawback that is important, of course, we have two types of models, the top-down and the bottom-up models. What is the difference between them? The top-down models consider the entire building sector as a single energy entity. So we don't need disaggregate individual components to calculate energy consumption. This type of models is not complex, but later we don't have the enough information to identify potential improvements in building energy use, physical design, or operational specifications. In the case of bottom-up models, normally we have an extensive database to constitute a set of buildings. So the model inputs are weather data, geometric data of the building, so shape, spatial position, and so on, and non-geometric data of building, envelope, occupancy, energy usage pattern, equipment loads, infiltration rates, back system types. This is necessary because we want to apply reduced order models or data-driven models, or combine different technologies or different advanced modeling tools to quantify each individual component and decide with justification what is better for our scenario. But in this case, it's necessary to calibrate and validate our model comparison to the top models. Here we have a similar table than in the case of payment maintenance. So this table shows the main data that is captured for developing the models and how that data can be used by associated agents. So here, in the case of the city components, normally we use a laser scanning or photogrammetry to create the elements for the models. But we need standard cadastral information, the spatial information, and how the monitoring of these techniques is applied. And this is interesting for engineers, architects, or city planners. In the case of indoor and outdoor environmental parameters, we capture this data because our interest is to determine the thermal comfort, indoor air quality, ventilation, but maybe how the weather parameters influence in our environmental quality. So here it's important the inspection frequency, how the monitoring is carried out. In the case of thermal comfort, we use a microclimate station, but in the case of indoor air quality, maybe we need another type of equipment and not only a sensor for the airspeed. In this case, we have the engineers and architects too, but we have the figure of the building manager and energy auditor. The case of the energy auditor, it's important to know how, when, what, and who use this energy in the building. And in the case of building manager, he need or she need tools to know how to control the building or how to improve or how to optimize the performance of the building. In the case of building fabric performance, the captured data is used for build quality and refurbishment strategies. In other words, normally we use quantitative infrared thermography or heat flux meter to characterize the materials of the envelope and to know the thermal transmittance, for example. And in this way, check with the project, and if it's necessary, to add the installation for the new or the future scenario. So here we use in situ analysis with geometric and non-geometric data. And this is interesting for engineers, building managers, and city planners. And finally, the performance of systems that are the equipments of all the subsystems of the building. The use of data is to determine energy consumption, type of energy use, what is the user's profile for each space, and maybe predict the thermal zones of the building, or to establish predictive controls of HVAC systems, for example. And here is totally essential to have real-time data and historical data. And this is possible if we have a building management system installed in the host of the building. If not, we have to incorporate this type of software with the controllers and sensors for each subsystem. And here the main figures are the maintenance staff and the building manager. These people is who make the decisions in the building, and for the reason they need tools to take the optimal pathways of improvement. Now we moved to the construction safety management, and we have like an hypothesis that is construction works are performed in an unstable and predictable environment. So we have to ensure that we have construction materials and resources in the flow of the construction work. And later, we need real-time tracking as a reliable tool to rescue people in accidents or to reduce occupational diseases. So in an integrated safety management systems, we need to identify the hazards, to establish clear roles and responsibilities between our employees and employers, develop and implement controls, perform the work according to the standards related to safety and environment issues. And later, we need to involve the senior management and workers in our policies to ensure that this safety management system is in line with our enterprise. But there is a problem in this domain. Normally, site equipment are a bottleneck in infrastructure projects. The productivity gap can be attributed to inefficiencies in the management of earth-moving equipment, a lack of performance metrics, and low level of digitalization and automation. Why we have a low level of digitalization? Because, as you can see in the table, we have a lot of core applications in this domain. And for each one, we have different types of technologies with different protocols of communications, different types of data. So if we want to interconnect these technologies, we have a lack of interoperability. Now we have a table like the other domains where is shown capturing data, use of data, requirements, and agents. Normally in construction safety management, it's interesting to know the dynamic position of the objects and the workers. So we need to avoid the collisions between worker and machine or machine-machine. And for this reason, we have to identify the disturbances in the work site and to collect that in real time. And the delay of the decisions is really short. In the case of the workplaces, we need also to record with cameras or video images or sequential videos from each case. In other words, if we need a set of images and we implement machine learning algorithms, it's possible to create an automatic or tool with awareness to make decisions in this case. Later, in the case of body vital signs or distributed environmental sensing, normally the use of data is to improve the worker's health and avoid overexposure to high temperatures or humidity values that can affect to the equipment and to the people. And here, the agents are workers, employers, of course, but also insurance institutes or safety coordinators. In the case of the health status monitoring of infrastructures, we distinguish the fact of bridges, for example. Normally, the life prediction methods can help to develop a maintenance schedule, but the existing approaches have a limited versatility and reliability. Why? Because the monitoring crack initiation of last structures is not feasible and system states must be assumed. In the case of digital twins, it's challenging because digital twins are only applied in the design stage or are neglected in the maintenance stage of large structures. So maybe in the future we have to incorporate stochastic fatigue models with continuous incoming information. But regardless the technique that we apply, the direction is the same in the management system. We need a database through an inventory. We need to do an inspection through monitoring and control systems, to do the analysis and decide what is the type of deterioration of our infrastructure, in this case, the bridge, and how we can improve the performance and the maintenance stage in the future. In this case, we have a table with short information because in the case of health status monitoring, it's important to know the geometrical data to characterize each component, the material microstructure testing to determine indicators, to assess material behaviors, to configure the microstructural performance of our element, and later the data related to operation to predict fatigue operation, collapse, what is the life of this element, which are the repair strategies, and later this data has to present a high quality because we need to create high fidelity models. And for this reason, it's important the type of monitoring and what are the inspection frequencies used. Normally, the agents that are involved are engineers, operators, or managers. And finally, we are in the traffic management, that is the last domain. And the models developed for road transportation management are not usually integrated and differ in number of dimensions. Let me explain. Here we have a table with different dimensions and the stages of a structure or element. So in the case of roads, we have the stage of planning, the stage of maintenance, and operations. In function of the model spatial scope, the time horizon, the time discretization, the frequency of the database, the type of model, is this static or dynamic, and the space discretization, we have different characteristics. So we have to decide in each case what is our network and what are the features of our network. It's not the same a lifespan of 20 years than 60 minutes. It's not the same navigation maps than specific addresses. The type of data or the volume of data differs a lot. In the case of Europe, we have TRIMIS, that is a Transport Research and Innovation Monitoring and Information System that use the part of STRIA. And is a traffic management system with an open access platform. In the case of United States of America, we have RITIS, Regional Integrated Transportation Information System. And in this case, the data is stored in a private cloud and disseminated by credentialed users. What is the main feature of this type of system? That we have an analytic platform for solving real-time complex problems, such as evaluation of safety and mobility, prioritization of investment decisions, measurement of operational performance, and system monitoring in real time. The type of data normally is traffic volume, incident information, weather data, how affects the rain, the sun, the snow in the road. We have transit alerts, vehicle locations, vehicle travel time. And the agents are normally the same public users, third parties, the National Weather Services, Public Safety System, the Departments of Transport. This is okay, but later, if we analyze enabled technologies, we have the same problem that we had in another domain. There are a lot of enabled technologies with different protocols, with different types of operation. So there is a gap for the future digitalization. Normally, the capture data is the status of the equipment and the status of the roads. We need to know how the roads are for the refurbishment. Here we can use building information modeling and later share the models to road authorities, contractors, transportation planners. In the case of equipment, it depends of is it static or dynamic, like traffic lights. Here, normally, we use the integration of different types of information. And in the case of mobile equipment, we need to the position, trajectory, and speed of vehicles, because maybe we plan a long-term purposes that is offline, or in terms of online, we need to establish operational purposes. And normally, we use black box platforms and in-vehicle recording devices. And this is more for road authorities, transportation planners, and researchers. After analyzing the domains that affect more in the operational stage of the infrastructures at urban scale, it's time to talk about future perspective that is focused on the use of digital twin for urban built assets. But what is a digital twin? Okay, normally is defined as a probabilistic simulation of a complex system that tracks current and past states of an entity. We need a replica of our physical entity. This replica contains a large amount of generated and stored data related to the life cycle of the physical system: design, construction, operation, deconstruction, and historical data and real-time data from sensors or from the inspection that the technician carried out is used to simulate different future operating conditions in a virtual system. In this way, we can visualize or analyze what happens in the future and how we can improve the situation of that scenario. Normally, we know that digital twins were more used in aerospace applications, but later appears in construction too. Normally, in the case of product lifecycle management. And we know all the benefits that represent digital twins. But when we talk about interoperability, we have several limitations. We have low automation of data exchange and technology maturity. We need to validate the individual components. We have a high variety of enabled tools and technologies. So what is the tool optimal to develop digital twins in roads or in buildings? If we don't have clear this, we have another issue: the propagation of measurement errors. Or maybe the data flow is usually unidirectional. So we have the data, we test the digital or virtual entity to the physical, but later we don't have the feedback from the physical to the virtual. So the cost depends on the know-how, the algorithm complexity, and how the data is transmitted to the model. Nowadays, the most relevant application of digital twins is the product lifecycle management, because the traditional approaches don't guarantee data traceability for different types of information sources or technical status. And the modern manufacturing present high demands of products, high quality of products, and rapid market response. So if we want to update quickly our system, we need a virtual entity to do test with minimal costs and minimal computation time. And in this case, if manufacturers apply or adopt digital twins they can incorporate circular economy easily. Finally, after analyzing the enabled technologies, the agents, how digital twins can be applied for built assets, and to understand the significance of each agent in the urban infrastructure system and how the agents can take actions, a stakeholder map is proposed. This can be seen in the right side of my screen. And we have the key players: European Commission, regulators, governments, transportation authorities, city councils, local administrations. The defenders, citizens, industrial associations, vehicle manufacturers, construction and road workers, for example. The latent stakeholders, centers of traffic management, production managers, demolition managers, city planners, agencies, and the audience: media, National Weather Service, universities, capital market participants. Why we distributed these 4 groups? Because we need to plot the influence of power of the stakeholders versus the interest and involvement of these stakeholders in the urban infrastructure system. So the key players or promoters have a higher influence on the project. They correspond to big investors or entities that make decisions and validate assumptions in the infrastructure life cycle. So we need to keep informed this type of people. The defenders are potential supporters that must be completely informed because they are frequent users, but they can make smaller investments. For this reason, there is a difference between the governments or local entities that are key players and the defenders that are citizens. And in the left side of this graph, the latent stakeholders are people, institutions whose needs should be met or anticipated because they have influence and power, but the involvement is low. And the audience are minor stakeholders. They should be monitored, but they present low stakes. And we need to adopt this type of graph for all the domains that we analyze. This is a general view, taking into account all the domains that we built during this presentation. But later, we need to analyze this type of graph for each one. So the conclusion is that the development of technologies at urban level can only be successful when each agent and player is providing its own contribution in a coordinated way. So the policies must be directed towards the collaboration. And interfaces must be managed to make interoperable subsystems. And now we move to the keynote speakers. Now we have different sessions about this type of topics. Dr. Sion Peck from the University College of Dublin, Ireland. Dr. Ryan Sale from Cambridge University, UK. Dr. Burcu Guldur from Hacet University, Turkey. Jason Datsanakakis from Sueco Group and is a PhD student in Netherlands. And Navi Musharbach from Università Politecnica delle Marche, Italy.
Okay, hello everyone. Thank you very much for inviting to this seminar and giving me the opportunity to present. So today, title I choose today is the developing the innovative sustainability management in energy storage system. So this presentation will provide with an overview of the research that my team is conducting at this moment. So it is about the innovative management in the sustainability facility. So my previous and the current most works are about the buildings and the roads. And this kind of energy storage system is very new to us as well. But I thought it would be a very good chance to share what is going on with our team. So before we start, I would like to just quickly introduce myself. So my background is the construction management, and I mostly focus on the infrastructure, not just infrastructure, all the construction projects, how they are complex. So try to more focus on the practical way, how to we reduce the errors, how we effectively collaborate with the team, the stakeholders, how we improve the productivity and the sustainability, and how we correctly predict the cost, schedule, or the quality. So I think, as you know, the Smart Market report from the 2017, so they done the survey to the participants, the stakeholders who were in the project with the digitalization, more specifically the BEAM, and they felt the 34% said that they had the fewer errors, 32% the better understanding, 20% cost productivity, 60% better schedule, 80% optimize on design. So this actually start from my journey, and I will just because I have the only 15 minutes, so today I will quickly just introduce what kind of the research we are doing. So the research, the SCAM is the Innovation Partnership Program. It is funded by the Enterprise Island, and there are three different streams that we can go. And the one that we choose is we do the feasibility study first, and then move to the main project. So we started the feasibility study on the 1st of April, and then we worked on that for the 5 months, and now we are about to start the main project. So now we are kind of wrapping up our feasibility study and doing some kind of paperwork. And as you can see in the right side, so this is our consortium. So this is funded by the Enterprise Island, and we have the Lumclon Energy. This is the developer, and we have the UCD, the research part, and we have the Hanwha Energy Corporation Ireland. This is the EPC company. So to introduce about the project, so we have two sites at this moment. So when you look at the map of Ireland, so Dublin is here, and we have Lumclon site here in the Plummer, and we have Shannonbridge site, which is in this Shannonbridge. So the project capacity is 200 megawatt, the battery energy storage system, and the project cost is 150 million euro. This is just the construction fee. The construction cost was 150 million, and the market is DAC 3 system service. So that is the delivering a secure sustainability electric system. And the EPC again is the Hanwha Energy Corporation Ireland. So the construction started on the 1st of October in 2019, and we finished on the December of 2020. And this BESS system actually start to operate on the July of 2021. So even I have only 15 minutes, I brought 2-minute video from the Simpsons. So because it's very early morning, so kind of warm up. Let's watch it together.
Seon, it's not possible to hear the video.
Sound is not coming?
No.
Okay, well, yeah, so I don't have the time, so yeah, I'll just describe. So this is how they try to get the electricity from the wind, but if they don't have the wind, it's impossible to get the electricity. So that's the actual problem what we are facing with this kind of project. So the managing peaks and the throughs becomes more challenging, and the target is to achieve the net zero carbon production. And in the past, traditionally, the fossil fuel plant was used to back up to provide a reliable and steady supply of energy. So what happened to our site was, in the last year, the island weather was very good, which means there was very few winds coming. So we had to use the oil and gas to produce the electricity, and then we save it to the BESS and they provide to the consumers, which is meaningless of using this BESS system. So what is the meaning that if we use the oil and gas to produce the electricity and then we provide to the consumer? So that was the problem, how we get the reliable and stable supply of energy. And another problem was approaching in terms of the construction management, the project management view. So the load factor, so the load consumption per month was very high because they needed the standby power to use this kind of system. So we analyzed from July 2021 to November, and the average of 340 megawatt hour was used for the standby power per month. So that was the problem. So we set the aim and objective for the feasibility study. This aim and objective is not for the whole project. So this is for the just feasibility study. So we aim to investigate and develop a statewide energy storage system management database and a proof of concept BS plan. So in order to achieve this aim, we established the three objectives. So the first one is to assessing the existing system and develop the sustainable strategic plan. The second one was to identify and developing the local knowledge and record, which means to make it easy to investigate the records of the past data. And the final one was to do the pilot test of adopting the advanced technology like ICT and the digitalization. So what actually the result, what we done was we focused on the historical data set first. So there were three categories of the historical data set. The first one is environmental data set, which we focus on the wind and the solar parameters. And the significant and critical data came from the Irish Meteorological Service. And we found that there are 25 weather stations in the island. So 20 in fully automatic weather station here, and the 5 manned weather station. From there, we can get the data of air temperature, rainfalls, wind speed, directions, and all this, and the sunshines. So one example I brought, so this is the randomness and nonlinear of mean wind speed and the sunshine duration of Dublin Airport. So Dublin Airport, there was one weather station, because as you can imagine, the airport, the weather is very important for the flights to take off and the touchdown. So one sample, so left side is the variation of mean wind speed. So months, so monthly, this is 2021, and we picked a sample as of May 2021, so you can see the day data, and we choose the one sample as a 17 May of 2021, so you can see the data difference in the hours. Same, the sunshine duration, months, day, and hour. And another data set we achieved was to get the data from the Sustainable Energy Authority of Ireland, SEAI, and the Wind Energy Ireland, Irish Solar Energy Association. And one of the interesting thing about the data from the SEAI was that they have the 3D map. And the one interesting data was they provide the distribution of current wind farms in Ireland like this. So this was very useful. And the second category of history data is the BS operational data set. So this is the actual data from the its actual project. So we found that during the operation stage, 60 to 70% was the inverter operation, and the 10 to 20 was battery charging energy, and the rest 10 to 20 was the service system for the battery, like heating, ventilation, air conditioning, like that. So what we found was 330 megawatt hour of standby per month. That's the 31,638 euro per month. So this was invested on July 2021 to November. So we can assume that these days the cost has increased a lot. So probably have increased maybe a double. Sorry. So, and the last one is to focus on the data of energy demand data set. So in order to provide the stable energy, so we need to know the right data, the right demand, right to predict. So we got the data from the International Energy Agency, IEA, and ESP Network, SEAI again, and Air Group. And this is one sample. So this is from 19 to 2020, the past 30 year of the historical electric consumption in Ireland. So based on this kind of data set, next we move to find the right research methodology. So first, we focused on the algorithm, the emerging AI algorithm for wind and solar energy forecasting. So we analyzed 127 past researches, mostly about the research papers. So for example, the first one, the artificial neural network, there were meaning research. When I say meaning, it's something that relate to our scope. So we found that 13 meaning research in the wind energy and 24 in solar energy. So that's total of 37. So that's how we found the algorithm, and we selected the 14 AI algorithm to analyze the back data we established. And the last part is about the asset management from the actual data of this case study. So what we focused on was the annual operational cost. And we found that 6 impact factors from the operation stage: the electricity, operation and maintenance, asset management, insurance, medium voltage electricity, this is for the reliable power source, and the trading fee and the advisor cost. This time, this is actual data, and the cost, I don't think it's appropriate to open this cost. So please excuse me, I just opened the percents. So as you can see, the 47% is electricity. The second one is 29 O&M AM, and 15 insurance, 4 medium voltage electricity, and the 2 trading fee, and the 1.6 was advisor cost. So as an example, what we suggest to our industry partner was the first one to change the logic of charging the electricity. So what this means is the cost of electricity from 2 a.m. to 5 a.m. is an average of 70% of typical price. So if they change the logic of the charging electricity, the electricity power rate cost can be reduced by 8 to 10%. And another suggestion that we can do as an alternative is to get a support facility to support the electricity. So like, for example, if they have the solar panel in their site, even in the other site or even in their roof, it will support the electricity, like standby electricity, and will give the cost reduced on their operation. So well, that was about the feasibility study we've done and we're doing. And just quickly, the future research about our main research, we will approach in two ways. So first one is management development, and the second one is the support from the digitalization development. So the management development, we will keep approaching about the change management, site level optimization, lifecycle cost analysis, maintenance management, retrofit, reconstruction, renovation. And the digitalization development will support this management development. For example, digital twins, laser scanning. Well, actually, we've done this laser scanning and the sensor, RFID, all those stuff. So benefits, I'll not go on the details. So it will, of course, benefit to our industry partners and to the consumers who will use this electricity. And to conclude, I think the digitalization and the sustainability is not one of the significant disciplines like the architecture or the civil, electric, mechanics, fire like that. So, and also there's no automation in the world where tens of thousands of data just come in one click. So, which means the digitalization is a data management or the data utilization process. So we, the engineers, must build the data correctly and must use it effectively and efficient way. So that's my conclusion. Thank you very much. And I will have a Q&A in the later, right? Yeah.
Yeah, thank you very much, Dr. Seung-Baek. And now we proceed with the following presentation. The discussion of all the sessions is at the end of this seminar.
Blanca, hi. Could you just confirm that you can see my slides?
Yes, it's perfect. Thank you, Brian.
Great, great. Thank you, and thank you, everyone. So my name is Brian Shiel. I'm the Laing O'Rourke Associate Professor in Construction Engineering at University of Cambridge. I've been here a grand total of 2 months, having joined from University of Oxford, so I'm in a new post. So today I'm going to talk about my work on developing new sensing technologies for underground construction. And if we look at infrastructure construction and some of the gaps, this is a huge market. It was valued at $12 trillion in 2019. And in the UK, there's a huge emphasis to build back better. But if we are to build back better, we need step changes in how we deliver our infrastructure. And we are seeing exciting advances now above ground. So, for example, modular construction, the use of virtual reality, AI for productivity and carbon reduction. And our argument is a lot of these exciting advances have not extended to below ground construction. So in a lot of the areas that we work in, measurement is not routine. We often work without design methods, and there is a distinct lack of digitalization. So there are real pain points when we move to underground construction. So to target these pain points, what we are doing at Oxford and now in Cambridge is our research on digital underground construction, which varies from subsurface building information modeling and digital twins through to intelligent tracking and automated calculation of embodied carbon during construction, smart construction elements, the use of AI to optimize performance. And when I say performance, that could be productivity or sustainability. And given the duration of this seminar, I'm going to focus my talk on the development of new sensing technologies and how we're using those technologies in our site monitoring and automation to really optimize how we deliver below ground construction and infrastructure. So to motivate my talk, I'm going to give you an example of some of the construction processes that we work with. So in the UK, this is a large diameter concrete caisson that we use for underground storage and attenuation tanks for the water and wastewater industry. They're also used as launch and reception shafts for tunnel boring machines. But you can see the construction process for this structure is a concurrent casting of the concrete walls shown here. And once wall construction is sufficiently advanced, excavators are dropped into the caisson and they begin excavating. And you can see this entire structure begin to sink into the ground under its own weight. And what I'm showing here is the actual video monitoring taken from our most recent monitoring project in Blackpool in the UK. So if we were to take that construction process in a little bit more detail, what I'm showing here is a cross-section of the caisson wall. And just to point out some of the construction features and the pain points that our industry partners deal with. So one of the most striking features of this wall cross-section is actually this tapered cutting face, is what we call it at the base here. The purpose of this cutting face is to essentially act like a knife to reduce that vertical resistance of the soil as that caisson drops or sinks into the ground, as shown in the video. So another important feature of the wall is this leading edge. This is a steel band that encapsulates the caisson. And the purpose of this leading edge is essentially to create a gap between the wall and the soil. And this is filled with a lubricant. And the aim of that lubricant-filled annulus is to minimize friction during the sinking process. So these are really two key features in the construction process. And that are largely for construction, not necessarily the long-term in-service behavior. So to get this wall into the ground, we rely entirely on the self-weight of the caisson itself, the caisson wall. And of course, resisting that are the soil resistances that act on this angled face, and friction resistances that might develop in the event that we get a closure of that gap or that annulus between soil and wall. So at that point, we get soil structure interaction or engagement. And so the process continues where we add another wall pour on top of a wall and the caisson sinks to achieve this new equilibrium given the soil stresses. Now the real pain points are, industry do not have a means of measuring these stresses, even though they are crucial to the design of the construction process. And we also have no design methods. So these are really significant uncertainties. And what that has meant is we have significant over-conservatism in these construction operations. And when you have over-conservatism, it means we're paying more for this infrastructure and the carbon cost is much, much higher. So our researchers really try to target this by developing technologies to measure these bearing resistances and these frictional resistances. So how do we measure soil structure contact stresses? Well, the way existing sensors work is you have an applied force. So for example, there could be a green normal stress from our soil. There could be black bidirectional frictions coming from our soil. And the structure itself is designed to deform under these applied stresses or under these applied forces. And if we were to carefully mount transducers somewhere in this deforming sensor, those transducers would create a signal reading. And in this way, we can calibrate the sensor. So by applying known stresses or forces, we can match that to the signal output. Now, there are a number of problems associated with existing sensors when we have tried to deploy these below ground. So the first one is existing sensors don't give us all of the information that we need as underground construction engineers to optimize the design. So we're not actually able to measure soil and water stresses independently. They lack robustness, so existing sensors are susceptible to water damage and electromagnetic interference. Again, makes measurement a little bit more uncertain. And of course, they're expensive. So existing sensors are very expensive because they need these intricate structures and wiring circuitry. So what we have come up with at Cambridge is a new patented design and build pipeline for a more sophisticated generation of force sensors. And what we have done is taken state-of-the-art advances in fiber optic sensing and fuse this with machine learning to deliver that more sophisticated generation. So what we use is, first of all, we use machine learning or mapping algorithms that allows us to go directly from the raw fiber optics to the required sensor outputs. And that allows us to use much simpler sensor structures. We also use optimization algorithms to optimize the pattern of fiber optics on these sensors. And this allows us to use, it's optimized for manufacturers. So it allows us to use much simpler patterns that are designed not just for performance, but also for ease of instrumentation and assembly. And of course, because we're using machine learning to do the mapping, they're well suited for new materials. So we're not limited to the linearity that we require from our metallic structures. So it opens up possibilities of developing ultra cheap sensors. And they're robust because we're using fiber optic sensing. It's inert. The possibility of putting these in for construction, but then leaving them for the long-term structural health monitoring is now feasible. And it's exploitable. So we're exploiting this technology through a spin-out company through Oxford, which is called Jenkin Technologies Limited, to deploy these sensors, not just in construction, but in other areas such as in robotics and in industrial automation. So we've been working hard in our lab to advance these sensors. We've developed an experimental prototype. You can see here, this is a crude first generation of our force sensor. But what you can see is there's a pattern of fiber optics here that's been bonded to the sensor. This pattern of fiber optics has been designed by our AI algorithm. So our AI algorithm, depending on what we want to measure, has told us this is the pattern that you need to be able to measure those forces. And then we have patented clips that we can mount those fibers in a matter of minutes and bond them. So we can build a sensor in minutes. And you can imagine then the soil stresses or whatever force we wish to measure, this would be the top surface here would be the sensing face. And we've done experimental validations. So what I'm showing here on the right are predicted and measured or targeted and measured 6 degrees of freedom forces. So we've got 3 orthogonal forces, so Fx, Fy, and Z, and 3 orthogonal moments. And it performs very well in all 6. What I haven't shown here is it also predicts temperature as an output as well, and that's how we handle the temperature compensation element of fiber optics, which is a very well-known pain point. So we've been using these sensors to transform construction in our own way, and this is a case study of that project, the video monitoring that I showed you, which is the underground stormwater pumping station in Blackpool. And as part of this work, we provided live digital feedback of the settlement and tilt of that caisson during construction, the soil stresses, lubricant pressures on that exterior wall, and of course the wall strains, because we're keen to know how that product is behaving during that construction process. And by going digital, it has allowed us to exert greater control of the construction process. So I'm just showing here a video taken from that monitoring project. So you can see our monitoring dashboards, this is our fiber optics here. As I move out of this monitoring container, you can see our caisson being constructed here. As I turn around, this is our lubricant pumping stations. So all of this has been connected. The lubricants get sent all the way through to a flow meter that I'm going to zoom in on here, which is an old flow meter, but we intercept the data from that flow meter into our monitoring to understand how much lubricant is being sent to the container. And then the lubricant is sent to a manifold that we've designed, which is sent to the caisson through a series of air-fired ports. And again, all of these air-fired ports we can control automatically depending on the soil stresses that we're measuring in the caisson. And aside from being a trip hazard, all of these hoses send into a spreader bar that we designed as well in collaboration with our industry partners in the wall here, this photo on the right-hand side that I'm showing. And what this has allowed us to do is optimize construction or the delivery of that lubricant to minimize soil stresses based on these fiber optic measurements. So we have been using this to really try and drive change and drive impact in industry. So what I'm showing here on the left-hand side is a photo of one of our tablets in the excavator during that construction process. I'm just showing a zoomed up image here on the right-hand side. In this case, we're giving the driver real-time measurements of the settlement and tilt of the caisson during construction. Because if the caisson starts to tilt, actually our platform tells him or her with red and green buttons where they need to excavate in order to recorrect that tilt. So in this case, green is pointing to what side of the shaft they need to excavate to recorrect that tilt. And that has had significant impacts. And just the latest project, we're able to save 90 tons in embodied carbon just through better designs and better measurement and optimizing construction, and saving over 150,000 pounds. And this is just through reduced material consumption. So it's a very, very simple calculation. And we're also speeding up sinking times by delivering information directly to the people that need it on site in real time. Okay, so to conclude, our argument has been in my underground construction group that we're seeing a lot of exciting innovations now in construction, but a lot of these are not yet permeating below ground. And for measurement, we really see fiber optics and AI as being an exciting opportunity to develop a more sophisticated generation of sensors to really develop that I guess, urban scale that Blanca mentioned below ground. And in a lot of our underground construction processes, digital engineering and rigorous science are really key to unlocking efficiencies by alleviating some of these pain points that we're encountering. So that's it for me. Thank you very much.
Thank you, Ryan. Now it's the turn of Burkut.
Okay, I'll try to share my screen now. Just a second. It seems like I just... Okay, here it is. Can you see my screen now?
Okay, it's not... okay.
It is.
Fantastic. Yes.
Okay, great. Thank you. Good morning, everyone. The topic of my talk was the use of data for road maintenance, but it was a very general topic, so I wanted to narrow down a little bit. Now I would like to talk about a project that we have been working on, which is the detection and quantification of payment defects using deep learning algorithms. So this is basically how we're using the data, which I mentioned, which is the image data, for performing detection and quantification of certain types of surface defects. As you can see from the image, what we like to do is whenever we take a picture, it might come from a surface vehicle, or it might come from drones or any sort of equipment that we can take our hands on. But what we like to do is try to understand what sort of surface damage that we have, and if we can quantify them so that we can give a reasonable idea about what is the condition of our pavements. So this is a study that have been performed by one of my students, Tuba, and she was kind enough to prepare the presentation for me as well. So I thank you, Tuba. I think she's listening. So let's start with the artificial intelligence. We know the developments that have been happening in this field. What we have been doing in this particular research area, the focus was first on machine learning, and then these algorithms have developed to mimic our sort of understanding about the world to generate neural networks, and then it's actually moved up to deep learning. So there are several things that we can do with deep learning if we have enough data to train and to test our specimens or for specific cases. One of them is classification and object detection and segmentation. So in this research, we have been focusing on object detection because we would like to get the idea of the defect as an object rather than just determining whether it's a crack or not, right? So it's a different sort of understanding about the images that we're using for defect detection. And also we would like to segment them so that we can understand where we are seeing that sort of damage and what kind of understanding we can get or assessment we can get out of this information. So for object detection and segmentation, there have been a lot of architectures that have developed over the years, and the most recent and effective ones we try to implement in our research. For object detection, it is FasterRCNN and YOLO versions. So there are several YOLO versions, and we have been using, I think, YOLO 6 and 7 now. We have been testing 7. And so the other algorithms we have tried as well, but they didn't give us as good as results as the first two ones. And for the segmentation, we have been using UNet algorithms. The most important thing about performing object detection by using deep learning algorithms is your data sets. So that's why I wanted to give this talk. So data set is very important. So we have been trying to find what are the available data sets online, and if we can use them to train these algorithms and then test them on different data sets. If you have been working with deep learning algorithms before, or any sort of neural networks or machine learning, you should know that whenever you train something, it is generally case specific. And if you try to implement that in different types of data sets, your accuracy or precision drops down fairly. So what we're trying to do was, okay, let's get as much as data we could get so that we will have a variety, and then our testing results will be better for any collected pavement image. So we try to find the available data sets first, and then we label the images manually. So this is the most tedious part of the process. You have to label the images that coincide with your needs for the data sets. So for the RCNN, faster RCNN, we use Pascal, and the YOLO has its own version. And also you can do image augmentation or image creation based on the data sets that you already have, if you don't even have enough data to train your exams, or at least you don't reach to the results that you are expecting to reach. So this is the software that is a generally used label image. As you can see, this is the example we would like to show. So except for pothole, as you can see, it is defined by a rectangular area. And then as you can see on the right-hand side, it is labeled as pothole. And here you have a crack, and this is a longitudinal crack. You can have alligator cracks or whatever type of defect you have, you can actually label them by any sort of software, but this is a label image. So labeling format, I just wanted to show you what they might look like. So the Pascal is a little bit more complicated compared to the YOLO format. YOLO is quite intuitive. As you can see, if you have certain identification for any sort of defect you have, 0 as being the longitudinal crack, 1 being the reflective crack, 3 is the pothole. If you look at the first line, 3, this is the pothole information, and then this is the coordinates of the bounding box that you are labeling them with. So as I said, YOLO format is a little bit more intuitive, but Pascal format is a little bit more complicated as compared. So the data sets we use for segmentation, as you can see, we have several of them. Crack Forest data set, Crack 500, Crack 3, GAP as version 1, and Deep Crack. So these are already available data sets which have been collected by different researchers and have been used in various research projects, and there are several papers on them. So, and their masks are already established, so we have been trying to combine them all and get enough image for our applications. So here are some results for the object detection models. As you can see, as the version, so I can say that for the previous versions as well, as the version of the YOLO increases, we tend to see better results. For YOLO version 7 case, the precision dropped down a little bit, but the recall, MAP, and the training time reduced, and the other ones have increased, obviously. So the overall result has been better. But as you can see, the precision is still low because, as I said, we have been training our data set from different collected data sets, and we have been testing them on different data sets generally. So it's a little bit lower than we expected. And for the segmentation, as you can see, but okay, so one other thing that I want to discuss was the training time. As you can see, the training times are still a lot. So for a certain type of architecture, like say YOLO version 1, it takes nearly 6 hours to train. So this depends on the machine that we're using, but we have been trying to use this in a very regular laptop configuration, so it takes nearly 6 hours to train. And the same thing happens with the UNet with ResNet 34, and it's 6 hours and 15 minutes. So Okay, so how we collected our own data and tested it. So we have been doing it with a UAV, a drone. As you can see, it's a Mavic 2 Pro. It's a DJI drone. That's a very commonly used. It's easy to use, easy to implement, and there have been many softwares to deploy these types of drones, and then you can select a pad and that will collect information for you. We have collected our data set from our university's campus. This is the campus view here, and these are the roads, and these are the locations where the images were collected, as you can see. So a couple of test images here, and these are the predicted defects on those text images. Most of them are quite good. As you can see, we have been able to detect the alligator cracks, and then longitudinal cracks are there. But one problem is, as you can see, the alligator cracks are not in total, so they are separated. So it's not a good combination, but the overall result was good. And here, a couple of results for the segmentation. We have the test images and the predicted test images. And then again, it coincides good with the original image. Okay, sorry for this slide because I have some Turkish titles on top of it, but the first one is the categorization. So we have, like, let's say longitudinal cracks, reflective cracks, alligator cracks, and potholes. And the severity is low, medium, and high, and we have the reference limits for those. And these are taken from, so this is a reference that we have been trying to use because we wanted to convert our findings into a map so that it will represent the general condition, the assessment of our findings. But this is a combination from different guidelines that we have been collecting and combining. So we have been looking at different DOTs and Turkish, US, and I think Canadian mostly. And so for the average crack widths, we have certain severities that are associated with a certain type of crack. As you can see, for the collected images, what our results will show. So this is an interactive map, which I wasn't able to show here, but it's an interactive map. What happens is once you do the data collection and then you process your data, you do segmentation and object detection. And after that, we are looking at the assessment criteria, and based on that assessment criteria, a severity level is assigned to that specific image. As you can see, the green ones are low severity, and obviously the red ones are high severity, and that gives you good information about how your road has been, what is the general condition of your road. And also, if you can click on the image, you can see your initial view and also your damage detected version of the road as well. So this is what we have come up so far, but it is still, so we have been still dealing with the map, and also we have collected several other data sets. So we're trying to improve the results of our detection as well, because still, as I said, the precision is a little bit low than we have been expecting. Thank you. This is my presentation. I don't think we'll be accepting questions right now, but thanks for listening.
Thanks, Burcu, for your contribution. Later, we can discuss the details of your presentation with other members.
Okay, I'm stopping sharing now. Thank you. Bye.
Okay, and now it's the turn of the following colleague. Yes.
Hello, everyone. So I will start sharing my screen. Give me 1 second. Super. You should be able to see my screen.
Yes, perfect.
Super. Okay, so hello, everyone. Thanks also for the invite to be part of the seminar today. So today we're going to speak about digital twins. You already see a few presentations related to data, sensors, how can make use of those data. So following those presentations, I think this is also connected. So digital twins, a new promising topic. Sometimes though it helps to define it more clearly. When is a digital twin something more than a 3D on a map? When does a digital twin add value? How do we get to it? What are its practical implications? We will try to discuss those things in this presentation. My name is Iason. My surname is a bit difficult, Giannakakis. I work for Sweco Netherlands, mainly as consultant in information management and ISO standard 19650 and digitalization from an organizational strategic perspective. So if we search in Google the term digital twin, then we get results like those. Point clouds, dashboards, 3D maps with data, some nice pictures, impressive, and etc., etc., etc. And at some point, maybe some of you might have one of those expressions like, wow, cool, impressive, I want this. Let's try to scan the information that we receive, because also some fancy picture is not always the true, and maybe things are even simpler. And there are many definitions about what a digital twin is. So for the next 10 minutes, let's agree on the following definition in order to be aligned on the same page. So a digital twin, to my understanding, is a digital representation of a real-world system that reflects real-time data from sensors to monitor, control, and optimize its functionality. And we use carefully the word digital representation because it's not a precondition that the representation needs to be in 3D. It can be a dashboard, it can be a building management system, etc., etc., etc. And the real-world system, we use the word system because it can be in a city level, so in an urban level, in a building, or in a small equipment. And there are many application fields. So besides construction, it's in modern farming, with plant digital twins, aerospace, energy, automotive industry, and many, many other application fields. But today, we're going to focus in the construction industry. And let's do what is the relationship between BIM and digital twins, because BIM is also often used. BIM is not a precondition to have a digital twin. However, depending on the scope and the needs, BIM can be the most efficient path to reach a digital twin. And let's see here an example. So when we design, we start with the concept design, we continue with the design, and after construction, we have the as-built model, where we have all as many dimensions in BIM we want, and different level of details, and we have a 3D model, let's say, with attached information attributes, where we refer to the dimension of beams. If we now continue during the operation, the maintenance life cycle of the asset, and we combine with real-time operational data, then we can do some what-if analytic scenarios. So combined with machine learning, then we get predictive maintenance. So if we combine all those things together, then we can say that based on the BIM model, attached with information from sensors, we have those possibilities, and we speak about the digital twin. So it unlocks many new opportunities. So we can visualize sensor data on the digital asset to monitor and control the asset. We can process those data to detect anomalies and automatically intervene in the system, do what-if simulations, and test the impact of those scenarios digitally, combine the live data and the historical data from the sensors with the machine learning to apply predictive maintenance. And all in all, this is an example of what we can have. We can understand better how our asset behaves. We can automate the building management system, for example. In this way, we can save resources in terms of energy, water, waste. We can reduce failure risks, decrease the operational costs, and create value based on the needs. And speaking about needs, okay, wow, digital twins. But when do I need a digital twin? I want this or do I need this? I need this when, for example, there are many needs, but let's say some examples. I need to know in a user-friendly way, if I'm from a client perspective, how my asset behaves. I need to automate processes, functions. I need to put some thresholds and control those processes automatically and automatically intervene. I need to get the trend about my asset and its behavior also in the future. What are its needs in the future? For example, in terms of maintenance, I have a building and I want to test several scenarios, as said before. So I want to test them without risk, cost, undesirable results in the digital twin. I need to know the indoor climate, for example, of my space and let the space adjust automatically. Good. Let's say that we need a digital twin now. What is needed to get to it? Let's start with clear goal and need. We need to know the why. Then it's very important to have the correct team. Digital twins, it's a multidisciplinary topic. Many disciplines can be involved. So it's very important to have a good team. So consequently, discipline or disciplines experts, depends on what we are looking to. A software package, if needed, sometimes needed, for example, for parametric design in order to connect a model with data. Affinity with the software, this is related to the experts, and affinity with data. Because as you saw in the previous presentation, we can have many data, thousands of data. We need to somehow to smart interpret those data. And that lacks some challenges. So again, know the why. When implementing something new, change management is calling. Take this into consideration. Many disciplines are involved. Set the minimum requirements that compose a digital twin, so to ensure that there is actually a digital twin developed. And we all learn as it's a new topic. Continuously we learn. So as with everything new, digital twin as a new concept as well, especially in the construction industry, make it hard to filter the information. Let's see some practical implications. From Asweco Netherlands, we work on the topic of digital twins. We have some digital twins prototypes. We have some projects, and we have some projects that have the potential to become a digital twin. Let's see a simple example. We have a bridge in the north part of the Netherlands. The goal is to the long-term health monitoring of the bridge, because it's from a new bio-based composite material. Therefore, there have been installed more than 200, if I'm not mistaken, fiber optic sensors. We monitor continuously the deflection, traffic load, bridge dynamics, environmental conditions. The sensors are visualized as bubbles to the right image. Beside the project itself, here's an example where the level of detail of the 3D model does not influence the goal. So you see a very simple 3D model, but we get the data, we get the insights. Second case, a motorway bridge in Arnhem in the Netherlands. Now this bridge is under maintenance. There we have one platform that you see on the screenshot. There we integrate different information, the 3D model as designed and as maintained to do the comparison, street view, map location, technical data attached to the map. And this platform has future capability to become a digital twin and visualize sensor data on the same platform. So you have everything in one viewer. So this has the potential. It's not yet a digital twin. Third case, the old church in Delft. The problem, the tower is leaning. I can see the tower from my window because I see in Delft. It's still there. And the sensors we monitor for more than 10 years, if I'm not mistaken, from 2011. We continuously measure the tower inclination, the groundwater level, the temperature, and the detachment between the tower and the main building. You see here some examples of sensors. And to the right image, you see the location of the sensor which measure inclination and the orientation of the tower. Excuse me. I'm a bit sick. What do we need to do? Set thresholds and monitor tower's inclination. Visualize the behavior of the tower in a user-friendly way. Correlate the sensor data and identify their dependencies between the variables. Identify the trend and predict its future behavior. The result. As you see here, you see the tower, our focus is on the tower, and the black shadow box of the tower can be the threshold. So in a visual, user-friendly way, we can see whether or not the tower is leaning more than the threshold that we set up. And the movement of the tower is based on the actual sensor data. We can combine those data to the 3D model through parametric design. So what we see here to the right image is the movement of two sensors multiplied by 50. So it's in order to be easily to see the movement of the sensors. And we can visualize the movement of the tower based on those data. This is the actual movement based on the historical data. And we can see it also in a 3D. So again, in an easy way, by color indication, we can say, okay, when or not the leaning of the tower is acceptable. So we monitor. All in all, we can have those data, excuse me again, on the dashboard. What does it mean? We can show how the asset behaves, what is the trend. We can put some thresholds when it's acceptable and when it's not. And we can make some predictions. For example, a prediction that the tower will be there for 20,000 days more based on some thresholds. What else? We correlate the variables between the sensor data. We can see what is the initial situation compared to the current. And we can train a model to do a prediction. And as you see, the orange or yellow, I'm not sure about the color, the line, the model is trained well, so the prediction is quite, we have a good precision on the prediction. So all in all, that was my presentation. Thanks a lot. And of course, we have in the end some time to solve potential questions. You can always reach out to me if you have any more questions. Thanks a lot, and see you in the discussion session.
Thank you, Iason, and congratulations for your dynamic presentation. I like it. And now it's the time for our colleague Navi.
Hello, can you see me, guys?
Yes.
All right, so let me share my screen now. All right, so is it here? Can you guys see it?
Yes.
All right.
Now it's perfect. Thank you.
All right. Hello, everybody. Thank you. First of all, I would like to thank all my colleagues who presented before me. Very informative and interesting work and content. So I congratulate you on that. And I would like to thank all the people who are attending the seminar at the moment. My title for my presentation and my thesis is Model-Based Emergency Management of Building. Just very quickly, I'm not going to go over everything. At the moment, I am a PhD researcher at the Università Politecnica della Marche in Italy, and Professor Alessandro Carbonari is my supervisor. And for further information and for further collaboration, hopefully in the future, please feel free to reach out to me via LinkedIn using that QR code. So I'm not gonna go through the table of content, but basically I'm not gonna go deep into the research in a very detailed matter. I'm gonna show the general overview of what I'm doing and how the process is done. And based on all the research that I've conducted in the past 2 years, what are the some future ideas that some of the attendees or researchers can get inspired from. So first thing first, as we all know, BIM, when you approach an engineer who has no prior knowledge in BIM, you ask them what is BIM, they just directly relate it to a software. So I just want to briefly say that BIM is a very big, let's say, cloud. It tackles a lot of aspects. And as we all know, in BIM, there are many dimensions, 4D, 5D, 6D that are related to cost, time, and sustainability. And then 7D, which I am working on, which basically focuses on facility management as a whole and its subcategories. Before I started with my investigation and conclusion, I started reading these books, which really inspired my path direction into the research. Basically, all of them are introduction to facility management, emergency management, SysML, and programming. So the first step in my thesis research is basically I call it literature harvesting, where I collected 120 research papers using specific keywords such as BIM, facility management, real-time management, and such. And I started categorizing them into the second degree. And as you can see here, that was a preliminary mind map. And based on such categorization and the research gaps and statistics, I concluded 8 main topics that can be potentially used for my research as a first step. And then with elimination and further analysis and investigation, we reached out to emergency management technology. And of course, these papers actually were categorized as well, like after reading them further, into categorized based on what is the main area of focus of the paper. So as you can see here in the pie chart, there are most of the papers are technology focused, which of course, which is clear. And there are a lot of papers that are core topic related papers. As you can see here on the right bar chart, you can see the core topic focus paper are what are they focusing on, as well as emergency management focus paper. Mainly they are focusing on maintenance, evacuation, space, and digitalization. And the technology focused papers are, I categorize them into 3 main categories: building information modeling, asset information modeling, and digital twinning. And of course, for every category, I realized that some of them have high intense concentration and some of them are minorly intervened. So I divided them as well. So then I started with, so based on all that, I started defining the types of emergencies that I want to focus on into my research. So I started with fire, and I read a lot about it, and then that was my first milestone. And then I had, after I realized that I'm gonna work with fire, with the type of emergency was fire, I had to define what type of sensors I need to use in order to detect a fire in the building. And then, of course, every country and every region, as a matter of fact, has their own standards. And we are very blessed as engineers and researchers to have ISO, that is basically focusing on BIM adaptation via facility management, ISO 19650. And then after all, when I started gathering all the standards, I realized that every country and region have their own specific standards. They are majorly all the same style, but not not 100% duplicated, let's say, for that. So for now, for the research that I'm working on, I'm focusing on the Italian standards. And later on, with the expansion of the research, we can adapt into other standards. And the other thing that I had to take into account is the algorithms, because in regards when the emergency status in the building happens, people have to evacuate. So it was the main question was how would we notify the users from which paths they could evacuate, and how in the fastest and the safest way. Therefore, based on further readings, we discovered that there is an algorithm that we can integrate within our system, which is called the Jigsaw's algorithm, where it would show you the fastest path to use in case of an emergency and the building has to be evacuated. So later on, after we concluded all the requirements and everything, the big question was how on earth we're gonna translate that to a programmer who has no knowledge in the field that we're working on. And we discovered that system modeling language is a tool that we can use, and we can produce layout diagrams where we explain the overall, where we can put the overall system, and the programmer can understand what we are aiming and we're looking for in order to execute the preliminary prototype, so we can build on it. And then, of course, the last point is how, like, the technology is integrated with the hardwares. What is required in order to adapt a real-time management that is accurate and we can rely on. So at the moment, we're still in the process of deciding how the notification for the building users would be acknowledged. So one of the suggestions is using the mobile app, but still it is under discussion and debate. And then when we gathered all these information and we concluded that matter, we asked ourselves, how is that going to be beneficial and integrated into the system? And the answer is very simple. It will, with all the information that we insert into the system and would be executed in the prototype, it can easily notify the common building users that there is an emergency and then you have to evacuate. And based on the algorithms and the calculations that can be scripted into the programming script of the prototype, it can notify the people from where to escape. So let's say, for example, Gladys from Human Resources is located in the northern offices. She will be basically evacuating from the north side of the building. Meanwhile, Tim from Finance is in the southern, let's say, in the southern part of the building. He would have like another path to evacuate from in a very safe manner. Maybe in the southern part of the building, the fire is still on, lit, and they cannot evacuate from that point. So the system would notify them to go from the northern side. So it's basically like a yes/no system, but in a higher complex matter. Future ideas. Based on the research that's been concluded so far, a lot of things are taken into account. So, for example, post-emergency damage report, where basically based on the reports based on the damage that is established in the building, we can generate a prototype that can produce, let's say, quantity takeoffs or like the list of the damaged goods in the building that we need to fix. as well as the construction scheduling. Like we can generate a schedule that would help us understand the duration to fix the damaged goods. Maybe automatic system where it would order the items that are damaged. Some researchers suggested when I presented my work in EC3 this year in Greece, where they suggested the idea of trying to unify all emergency evacuation strategies and standards on a global scale and have like one solid unified system that you can use, as well as using the software to have solutions for future preventions. Like if the fire occurred in a special case scenario, the system can suggest future solutions in order to prevent it from happening again, as well as simulation of emergency circulation as well. And last but not least, explore other types of emergencies. So in my case, I focus on fire. Maybe my research can inspire and further, and other colleagues and future researchers can use the base in order to adapt other types of emergencies, such as earthquakes, flooding, contamination, and many other things. And thank you for your time. And if you have any questions, please let me know.
Thanks, Navi. Now it's the time for the discussion. You can start. What do you want? Alessandro, if you want to say some words.
Yeah, thank you, Blanca. Yeah, I would. Okay, in my opinion, the main purpose of this meeting is we have started from a white paper. We put together some interesting contributions by five speakers. So yeah, I would think of the overall picture. What I see, my point of view is that we had 5 presentations. Maybe the first, if I have to classify the presentations in a very broad way, I see the first 3 ones were about infrastructures. We talked about energy production, underground systems, and also road management and road maintenance. And the other 2 presentations were a little bit more general about digital twin, their role, and some applications. Some were about the monitoring of structures and buildings. The other were the last one was about fire emergency. So this application to fire emergency. So yeah, I see these very big groups. I'm wondering whether this could be a suggestion on how to manage a possible follow-up. What do you think, Blanca?
Your definition or description about the sessions is absolutely correct. And I think that now it's the time to participate the other members of the seminar. For example, what was your impression, Silvio?
Sorry, I was about to drink something. Sorry. Well, probably the presentation that is probably closer to me is Burka's presentation, simply because we've done some similar work using object detection, and in particular YOLO. That time was YOLO 5, so very interesting to see that you're using 6 and 7. You experimented with 6 and 7, which is quite nice to see. Yeah, I mean, again, it's the first time I kind of part of this group, and it's very. I agree with Alessandro that it's presentation were kind of varied. So the first 3 were more about the kind of infrastructure and construction, with the other 2 were more about simulations and the more digital side of things and BIM and all that. I don't have any comment really. I'm just talking like that, and very interesting set of presentations. I would be interested to see a little bit more about the white paper. I don't know if it's finished, if it's halfway through, if it just started, but it would be nice to have a look if it's possible.
Yes, the white paper was finished last year. This year was the part of marketing of this white paper, and it's accessible by the web of the European Council of Construction. But I can send the link by email if you want.
Thank you. I'll have a look. Thanks.
Okay, now I have a question for Urku, because it was an interesting topic. I apply more infrared thermography, but you apply other type of tools. So do you have problems with the autonomy of the drones when you do the analysis of different roads near to the campus or in other cities?
Okay. Yeah, it was a problem, especially so for the campus, it was a huge problem because we're living in Ankara, which is very close to all the military bases, so it's the capital. And we had a couple of signal processing issues with that. So we weren't able to generate a flight path and stick with it. Rather, we used manual control, which was hard enough to extract physical information because we weren't sure about the heights because it was manually controlled, basically. But out of city regions, it was a little bit easier because the Pix4D program, we were able to generate a flight path, and it has a constant height with respect to ground. And we know how many pictures we're going to be collecting from a certain region. And then we have several key points where we made the measurements so that we can actually convert our data into physical quantities. So yeah, in some regions it was really hard, but then the other regions was really, really easy to operate the drone. For your questions, I don't know if that answers it.
Yes, thank you, Urku. And in the case of Brian, when you expose your project, it's expensive to install all the sensors. You can take advantage from this installation for another project, or each project needs a new budget.
Yeah, so that's a good question. So I think that is a pain point that we have identified, that in the underground space, it can be difficult, time consuming, and a bit of a pain for the site team to install sensors in some of these locations. So what we've been trying to do is develop our sensors to be ultra cheap. So some of them can be sacrificial. So you can put them in very, very simply. It doesn't really bother the site team, and then they can be left in as a structural health monitoring package, which is good for the contractor because they sell that as an added value for the client. And then some of them can be reused. So it's something that we've tried to focus on with development of our sensors. So our sensors cost like maybe £100 each.
And in the case of ESON, you put sensors like Brian in another type of infrastructure. So you showed the example of the cathedral.
Yes.
But there are another examples similar to this building that it's possible to have the same model or the same type of code for other applications, or do you need to adjust the code for other type of buildings? I don't know if it's possible to take advantage of the past projects for new projects.
Well, it's a good question because I forgot also to mention something. I said also something about team. What you saw about the church, everything that happened, the visualization, the data interpretation of 10 years data, etc., happened in 6 hours. So it's a knowledge that you get, but the most important is to have the correct disciplines in a team. And why it happened in 6 hours? Because it was organized hackathon to see what can we achieve with different teams internally. So I think this experience can be used also in future process, and actually in terms of investment, like how many people you put working, it's quite cheap based on the results that you can get. And the sensor, I don't have any knowledge about the cost with installing the sensor, etc. It's a bit old project because it was installed 10, 11 years ago. So I don't have any idea about the cost. And yeah, but I think answering your questions, yes, you can make use of the experience that you get also for future projects.
Okay, so maybe in the future it could be interesting to create like a matrix of priorities, and in function of your object or your equipment or the building, create levels of prioritization in terms of cost and in terms of team, if it's necessary multidisciplinary team or not, and maybe the type of technology that you can use for that.
Yes, please.
No. Yes, I'm told.
I think then, if I understood correctly your question, then is also what are the needs from the client. In this case, the client is the municipality of Delft. So depends on what the client wants in terms also of costs, analysis, etc. If I understood correctly your question.
Yes, you understood correctly. And now we have a question for Nabi. So Mufid and Al-Nadi asks, will the prototype will be tested and obtain readings of accuracy?
Actually, that's a very good question. Actually, yeah, part of our research, like in the upcoming milestone of the research, when the prototype is generated and executed, there would be actually some tests, and based on the testing, we will obtain accuracy rates, and based on the accuracy rates, we can conclude and state whether the prototype is, if there are any challenges that they should be taken into account for the prototype or not. That's a good question. Thank you for asking, Mufid.
Okay, now it's the turn of Dylan Durmus.
Hello. Hi. Okay. Thank you for the presentations. They were all very inspiring. My question is for Nabi, and I'm wondering how the programming will be done for this emergency management. So maybe he can explain us more about the program system of the software. Thanks.
Thank you, Dylan, for that question. Actually, in regards to the system, we first concluded the overall system and how it's going to work. So we are, let's say, in the pre-final phase of generating the drafts of the layouts that we're going to use to start programming. The programming language is we still did not determine 100% what type of language we're going to program the system into. But most probably, based on my prior experience in my master's degree, we're going to work most probably on Python. And when the prototype is generated, we're going to start at the very, like the most popular, let's say, software or the common software, Revit, to do it as a plugin, and we can start testing it and see what are the obstacles and start adjusting within. So thank you, Dylan, for your question.
Semiao, okay, thank you. Semiao has a question for Burcu.
Yeah, thank you, Blanca. And sorry, I was typing the question there, but something wrong with my keyboard. So I will just ask a question. And thank you for your presentation, Professor Burcu, regarding your road damage detection. And just for the curiosity, how large was the database you used for developing the CNN? I'm wondering because.
Yeah. Sorry.
Yeah, please.
You wondered because what?
Yeah, I'm wondering because I can see that you obtained a very good accuracy, very good result from your CNN. But so I was wondering how large the database was you used for developing this CNN.
Yeah, it was not that big actually. We had a lot of images, but what we tried to do was to select the best training data set out of it so that we will have a range of defects on our hands. I think it was 1,000 and then 1,500 or something for the training. And then we had several other for the testing as well. So it's like 70% or 80% to 20 to 30% of it. But as I said, what we did was we also generated, we used augmentation as well. And also there have been, several data sets with thousands and 10,000s of images. But what we did was to select the best out of those data sets to train our algorithm so that it will work a little bit better on the newly collected data sets that we are obtaining from certain locations.
Okay, thank you so much for the answer.
And also, sorry, it's just like a plus thing. So we didn't want our algorithm to take too much time to train as well. So that was one of the concerns of my student. So she wanted to keep it in a manageable duration so that she can actually work on the other topics as well.
Okay, thank you so much.
Thank you, Senamburgo. We have a question from Fifi Shukri. Sorry.
Yes, hello, hi, can you hear me?
Yes.
Okay, I have a question to Nabih Msharbash. So basically, I wanted to ask if the BIM model level of detail restricts the prototype performance, basically.
To be honest, okay. I didn't think of that, but actually that's a very important point. Thank you for mentioning that, Fifi. Basically, theoretically speaking, the lower the level of detail of the BIM model that is going to be linked into the prototype system, the most probably, the higher the probability of not giving accurate readings. However, it does not. However, based on some research papers read prior, it does not mean that it is going to be the main aspect. So maybe the BIM model itself can be tailored for just detecting just to add the details that are needed for the system to operate fully. So it's a good question. Thanks for asking.
Thank you.
Okay, Seong, I have a question for you. In the case of your proposal, it's possible to do the implementation in smart grids?
So small.
So
sorry,
I understood that your proposal of energy storage system was for buildings?
Actually, that's the battery energy storage system. So when you get an energy, the electricity from the wind, so it keeps the electricity into the battery. So it's kind of a storage that the battery is inside. And the thing is that doesn't have like pipes or duct like the buildings, but it also needs the services to to make the temperature appropriate for the batteries. So they do have the HVAC system as well. So which means they have the structure and the service as well. So that's the thing that we can consider during the construction and mostly during the operation stage, how we manage correctly to effectively on that. So that's the focusing what we are trying to do. And to support that the management development, we are going to apply the digital techniques. And we're actually doing the feasibility study. We've done the 3D scannings for that. And so in the main project stage, we are going to more work on the details, more high level of details. So LOD is more higher on that, things like that.
Okay, thank you for your acceleration. And I don't know if there are more doubts or questions or between the colleagues.
Nabi, did you raise your hand?
Actually, I have a question that was sent to me by my colleague who couldn't make it because he have a meeting now. So I have a question to all the guest speakers. Basically, the question is how could we simulate the industry to speed up the process of digitalization with all these different softwares or solutions available on the market if there are no mandatory criteria for using these digital solutions in construction or any other infrastructure projects? The question is for everyone. So anyone feels things would like to answer, please go ahead.
What, if I can speak, what do I see from the industry perspective? Usually it's client-driven. So first the need is created, and then we try to solve the problem and satisfy the needs. Or we need to invest our money in order to create a prototype, show the potential to the client, so the client is aware and maybe asks back. So it's those two ways, as far as my knowledge. I assume for academia is the relationship is not industry client, but academia with foundings, but yeah, you know better. Or even clients again, because also the academia has cooperation with industry. But yeah, anyway, it's not like my expertise in this. Yeah, but from the industry, I think is, let's say, client-driven. Mm-hmm. And this is also about change management.
Interesting. Can I ask a follow-up question?
Of course.
Yeah. From your experience and knowledge in the industry, are you do you think the industry now are like, let's say, the construction industry, the leading industries, the leading firms in the construction industries are investing like, let's say, the healthy amount of time and money into the research, like to see what type of prototypes can work for them, or you see like they're still in doubt and they are not getting into that let's say research risk for them because there is money involved into the trials?
I think it's 50-50. So also from the case studies that I saw is 50% things asked by the client, especially when we stay on the monitoring. So those are client wishes. So in this way, they invest also in digitalization, which is, of course, very, very important. The other half, with the church especially, is our investment.
Uh-huh.
In order to propose, okay, this is what can be done with such a low cost. So I think the truth is in between. It could be better. But I think also a pitfall is that there are available in the market many solutions, unlimited solutions. If you go like to a conference, you see so many products about digital doing. So it's at some point maybe it becomes even confusing.
True. And unfortunately, based on the summer school we had in Greece this year, for example, the sponsor company is called Costain. They actually were motivating us to do like sales pitch and to present ideas. However, the thing is that it's still unfortunately it's still undetermined that companies are dedicating, let's say, some hiring researchers, let's say a small department in order to contribute for that. It's basically they're outsourcing, or if there are any ideas from an outer researcher, they would just get him, give him like his like a lump sum amount of money to buy the idea, and then they will just hire their own team. So that's unfortunate. And I just wanted to see your point of view on that matter.
Yeah, I think that's very important. The work under Alessandro, connecting the industry with academia and association, is maybe a way to a win-win way in order to continue further in this topic somehow.
Exactly. Yes, I agree.
Yes, I agree. Yeah.
Yes, because in the case of universities, we have to promote more the tech transfer to the market. And in this case, it's possible to have the industrial as clients. Yeah. That maybe now it's not the best way to do research, because we do a project and later we present our results in a scientific publication or something like that. But that tech transfer is in the secondary pathway in our career, and in the future, it should be in the same level than publications, I think.
Yeah, and actually, I've also realized because of post-COVID, a lot of industries that were actually focusing on dedicating some research and contributing with, let's say, investments on some prototypes or any other methodologies are now no longer in process, such as in Boston Consultant Groups, where they target every year some specific amount of budget where they can contribute for research. But due to the economy situation now, they don't do it. So as well, the economy is actually affecting the research and the progress of ideas and contributions whatsoever.
Okay, we have a question from Jürgen Koeberlein. Sorry for the pronunciation of your name.
Jürgen Koeberlein, hello and welcome. Nice to meet you. Thank you to Nabi Morbasha for your nice presentation. I have also a question to you. By the way, I know Nabi, it was one of my former students here in Würzburg at the university, and I am very happy to see you as a PhD student there in Italy. Nice to meet you here from Germany. And one question is from my side. I would like to ask you if you can join, if we can collaborate together in this, because your presentation was a model-based emergency management of buildings. I'm also here in Germany, on the one hand, at the university. On the other hand, I have a company in exactly this field for energy development, for the building technologies and so on. And I do also workshops in Jordan, as well in Amman and in Ukraine, in Kharkov. I'm there a professor at the university in Kharkov, at the National University. And one question from my side is, can we transform this idea of the based energy management of buildings to the energy sector? Because one big question here for Europe, for all countries here in Europe, is how can we handle the present energy we have now, and how can we optimize the energy distribution in a building, for example, in a public building, schools, at university, and how can we control it via smart home? And one idea from my side is, can we transform your ideas in a workshop, in additional things, and can develop it in a little bit in this direction?
Thank you, Mr. Jürgen, Professor Jürgen, for your time and your question. And to answer one question at a time, in regards to the collaboration, for me, I'm more than happy to collaborate. But yet again, the decision is taken by our research team. My supervisor and co-supervisor, Professor Alessandro, is with us now, so he can weigh in on the idea. And in regards to the energy, part of your question, I don't have the full knowledge in regards to sustainability and energy. However, in BIM, a lot of possibilities and ideas can be done and implemented as long as the system is fully understood and defined, and the process is working properly. Then I don't see any problem adapting within. I hope some of my colleagues can add to my point if they have the knowledge. And thank you.
Okay, Alessandro, do you want to say something?
Yes, I just thank you for your interest, Jürgen. I see right now the work on AV is mainly concerned with the emergency. Emergency is different from the regular management of buildings. How do you prepare for, or how do you manage in real time something? That's his. But our approach is that this is an excuse from him to get some specific skills in the field. Once he has finished, of course, with this experience and this particular application, I am confident that the skills and his capabilities could be reused, of course, also in another similar field, because the basic skills are all the same. And we will be happy to provide you with updates about his advances, the advances of his research. Thank you again.
Thank you.
And now, if we don't have more questions, maybe it's the time to close the first online seminar of this technical committee. Thank you very much for your participation and the collaboration and contributions of our colleagues and keynote speakers. And that's all. Thank you very much, and see you soon.
Okay, thank you.
Thank you.
Bye.
Bye.
Thank you.